information on sense. And so okay, and I just okay. So what this would allow you to do.
I'm not clear where the echo is coming from.
Are you unmuted?
I am muted.
You have the audio on your computer completely.
How do you do that? Should do it this time. So.
So you have your particle counters, and we were comparing between the expensive one and the less expensive ones. The thing that we weren't sure about is that the expensive version came with 2 different versions, a fan version and a pump version. The pump version was the one they had built for flights, and the fan version was the one they had built for ground bench tests. At the time, we were wondering whether or not fans would actually be suitable to get particulates to flow through the systems in the stratosphere. And so the lower cost systems as a default generally only come with fan systems because they're made to be used in ground-based HVAC systems to measure pollution and things on the same sort as that. They're not made to be used in a rarefied environment. However, we were not entirely sure what sort of effect this would have, and we were having problems understanding with our short duration flights whether or not we were actually not getting any data, or if our data was good, or if our data was fake because the system was trying to figure out what it was doing and it wasn't actually counting any particles. And so what we did is we took the really expensive system, we took a really low cost system called the PMS 5003, and we took a middle tier system called the AlphaSense N3, and we put them all in a box. And we took apart the expensive one and put it back together in our smaller container. We didn't have to take apart the other ones because they were small enough, and we had a system inside to run them all simultaneously and collect the data and save it to our system. That would allow us to directly compare each one for a long duration task in the stratosphere over time. And we learned a lot from this. First of all, we learned that fans really don't work all that well in the stratosphere. This is something that maybe you could have guessed, but it's actually really difficult to tell for sure. And so this provided our invaluable experience with that. It also raised a lot of interesting engineering concerns that we hadn't really considered. For instance, the fact that we were so worried about heat loss that we actually ended up overheating in the stratosphere because the stratosphere is warm and there isn't a lot of air to get rid of heat that is being generated by your system. And so we got to learn a lot of really, we got to go through a lot of really interesting engineering challenges that we weren't expecting, which was a great learning experience, completely separate from the science that we were trying to accomplish. And so this actually led to us having great development in our engineering goals for the system as well, including our first attempts at making something like a PCB to put all of our stuff on board as opposed to hand wiring all of our systems directly. This isn't a requirement, but this was something that was incredibly beneficial for us. It also jump-started my personal knowledge and how serial communication works, which ended up being invaluable later for interfacing with the M3, which was the best of the 3 systems that we looked at. We were able to modify it with different ways instead of fans in order to flow through the system and interface with it in a way that allows us to actually count particles now. Other programs that have worked on this is the University of Maryland program, UMD. They were actually under the same umbrella as us, but they were testing turbulence. And so they had a few different hot wire and cold wire sensors on the system in order to measure what was going on. This program has been used in a lot of different ways. The different University of Minnesota program, the SmallSat program, actually tested one of their cube satellites on the HASP platform as a near space environment. They're using it to test their communication systems before they launched into space. And so what they did is they actually used the large box size payload that you see here. This is a small payload. There's also the large ones. But they used a small payload like this to essentially put a CubeSat up. And they wanted to see how the CubeSat would interface in an environment where it's being really heat tested, really stress tested, and not able to communicate directly as normal. However, they still had the backup communication system that ran through HASP to test everything. And it ended up being integral to their development of their communication system for the Socrates satellite. Other groups have used it to measure ozone levels. Other people have used it as a telescope platform as a way to see things higher in the air. It ends up being a really interesting science program. And so what they're targeting here and what they're most interested in are programs that necessarily could not be done without a HASP program. And so you're looking for long duration stratospheric flight, if you're looking for really interesting engineering challenges for students, and if you're looking for a way to really push the bounds of what sort of things you've been able to do on local bloom flights, this is definitely a program for you. So this is jumping over to a different presentation that was given a few weeks ago. From the high altitude student platform group, this provides a little more detail of what they're exactly doing and what they're looking for. It's an annual flight opportunity. They have a few different pieces of documentation that you need to generate throughout the launch timeline. The first thing is the filling out the request for payload in November and essentially sending in an application. Then they'll accept your application, and then you need to present a whole bunch of you need to prep a whole bunch of integration paperwork as well as your payload for integration in July. And what integration looks like is you're actually putting your payload on that gondola for its eventual flight. And so you have to be able to pass a series of tests that they set out, including communications tests, low pressure, high temperature tests, low pressure, cold temperature tests, as well as just long duration survival of your payload. Then you have the actual flight, which you can choose to attend or not choose to attend, but you can control your system virtually. And then there's also the final report, the final science report, where you discuss what you've learned and how you were able to figure it out.
2 minutes.
So this is what the payload actually looks like. It provides up to 30 volts of power, provides downlink telemetry, and it provides live streaming of all the videos. You can see what the gondola looks like there. It's quite a beast. It flies under a very large balloon that we could not possibly fly on our own. If you're looking at this and you're like, wow, that is a lot, that's a really cool program, but it seems really, really intense. We'd like to try something on a smaller scale first. The University of Minnesota Space Grant Consortium also provides a lower scale version of this where it will allow you to hitch a ride on one of our ballooning systems. So this is called the BABS program, or the Build a Blueborn Stratospheric Spacecraft program. And what this essentially allows you to do is present a payload for colleges and pre-college groups annually every spring. You will contact Dr. Flauten about it. You'll apply for your inclusion. You'll provide progress reports and a flight readiness report the same way that you would do it for HASP. And then you have a day-long balloon flight in late April or early May. And then you provide a final report or promotional video. And so it's sort of like a HASP junior on a lower scale that allows you to just use a normal ballooning flight. This is a great way to get experience with stratospheric ballooning in the first place, or to even prepare for something like HASP in the future. This has been a really brief crash course into HASP and how we used it and different benefits for it. I'd be happy to take any questions you guys might have now. Are there any questions about HASP, about BABS, or about our experimentation on HASP? All right, perhaps any questions about how you can use it? Yeah?
Is the BABS program, is that run out of the University of Minnesota, and it's like a smaller thing for high school students? Am I understanding that right? And the other one is a national program?
So the BABS program is for high school or college groups.
Okay.
It's run with Dr. Flauten through the University of Minnesota arm of the Minnesota Space Grant Consortium. And so essentially what we would do is we take you out on one of our ballooning flights where we launch smaller stratospheric balloons with a smaller payload tolerance and essentially do a launch here. And so we allow you to get a ballooning launch without actually having to have the know-how or the experience on how to do a ballooning launch. Okay. It's a great way to gain that initial experience and understand how they work. And it's also a great way to get a science payload up if you're not really wanting to worry about the logistics and the details. Very cool. Yeah.
So how did the 3 sensors pan out? Did they
on our
figure
system?
data?
So we found out that the LOAC system only works with a pump in the stratosphere, which is something that we guessed, but was not in any of their documentation. And so the fan-based system really just didn't work in the stratosphere. The PMS 5003, which is the lowest cost model, was making up its data. When it didn't have enough information, it was trying to extrapolate what data it had, what data it should be getting. But because it was tuned for an HVAC environment, the data that we were getting was nonsense. The AlphaSense N3 actually wasn't working super well past a certain altitude, but its data remained true all the way through. And so we thought that its sensor system was not trying to do any extrapolation or interpolation. And so through our own modifications, we were able to increase the flow through the system and actually get accurate data up to the target altitude that we're looking.
Okay. Any last questions? All right, let's go ahead and thank our speaker again.
Thank you so much.